Yeah, thank you. My name is Andreas Bogk. I'm member of the CCC since forever. I'm also principal security architect at HERE, which is Nokia's Maps business. And I've learned about how buffer overflows worked sometime back in the 90s, and had a bit of fun exploiting that, and it became old pretty quickly. Apparently for some people it's not, and people are still doing it. I rather went into researching what can you do against bugs instead of just browsing your source code and looking at every line and tediously poring over it, trying to find all the bugs. And I soon realized back then that I just don't want to write in a programming language that has buffer overflows, which is an architectural measure. So the approach I'm taking against security problems is one of trying to find the root cause of a class of vulnerabilities and trying to address that whole class of vulnerabilities at once by choosing the right architecture of your hardware, software, programming language, program design, etc., etc. Now it sometimes happens that you actually have to use C, and I've recently discovered a line of interesting research that looks into what you can do about real-world existing C software. I always wondered about that, by the way, so I had the chance to talk about one of the C language standard authors, John Gilmore, a while back, and asked him, you do realize that you could have written the standard in a way that buffer overflows wouldn't happen? And he was like, yeah, but it was the late 70s and early 80s, and computers weren't so fast and didn't have that much RAM. But we carefully designed the programming language in a way, we carefully designed the standard in a way that you can write a compiler that doesn't have any buffer overflows and still be standards compliant. So that seemed like an interesting approach to me. So, but first let's recap at what we're talking about. You probably all see what the problem here is, right? Anybody who sees what the problem is in that code? Anybody speaking C here in the audience? Some. So for those who don't, or too lazy to raise their arm, I'll just recap. We have a buffer here on the stack of size 16 characters. We pass in an argument, which is a pointer to a character, and we just copy into that buffer without checking for the end of the buffer. So if you put in something here, it's a zero-terminated string that's longer than 16 characters, we write into some area of memory that's officially undefined. And you all know how that goes. If you write across the stack, you have a stack overflow, you can write into the return value, you can use that to trigger code execution in your code, which is what you don't want. So hackers give situations like that a lot of names called buffer overflows. They might call it stack or heap overflow depending on what part of memory you overflow. They might even be called integer overflows, although technically the overflowing integer only breaks the bounds protection, and again you have a memory overflow. If you look at the scientific literature that looks into how to solve those kind of problems, they call that spatial memory safety. So because you're writing in the wrong part of the memory space. And it's a very common problem. You still get problems like that. You remember Heartbleed? You remember the GNU-TLS problem from yesterday and the last 10,000 or so CVE entries. But that's not all in terms of memory security, right? You also have situations like that. Actually, two different instances of the same kind of problem. Like we allocate some piece of memory in the heap, then it's freed, and then we access that freed memory, and then we free it again. Actually, two problems here. First one is a use after free vulnerability. So I use a part of memory that already has been freed. It's no longer properly allocated. And here, that's a double free. I call free again, which also leads to all kinds of interesting effects, and it's not a good thing in general. So, of course, scientists have a name for that as well. They call that temporal memory safety, because it's the wrong time you're accessing memory. It might be valid memory at some point, but the moment you access it, it isn't. It might not yet be, it might be no longer. You're accessing memory that's not okay. So what can you do about it? One already mentioned, use a safe language, right? Don't write C. There's that great programming language that is called not C. And yeah, really, folks, there aren't many reasons left to actually write C. So some of the things I can think about is you're writing a microcontroller that has only 16 kilobytes of RAM. That might be a good excuse to use C instead of writing assembler. You might sit on a ton of old code that you need to maintain, that you cannot completely rewrite in a sensible time, and you have to do modifications. That's a reason to use C. Other than that, not much exists. Maybe kernel drivers in Linux, but seriously, use an operating system that's not written in C. Oh, sorry, it doesn't exist yet, but it will. It doesn't exist anymore. There used to be OpenGenera, which was completely written in Lisp. So that's a way out, but you cannot always take that way out. So the next common thing people do is applying mitigations, address space layout randomization, data execution prevention, stack canaries. They all share the same trait. They don't prevent the memory overrun. They don't prevent you from writing to the wrong part of memory. All they do is give you a way to make life for the attacker more interesting, right? So, in the good old days, in the stack overflow, you would overflow the stack, write onto the return address, function would return, you could jump to your buffer, and boom, code execution. These days, it's a little harder. There might be a stack canary in the way. Your buffer might not be executable, so you have to build ROP chains. But all those mitigations have workarounds. Like the workaround for ASLR is usually either finding a piece of memory that doesn't vary. On Linux, have a look at the syscall entries. They're all on the same page, and they give you enough gadgets to get going to call syscalls, and that's all you need, essentially. Or you have a read vulnerability that discloses addresses of memory that you can then again use to build your ROP gadgets out of. Data execution prevention, DEP, I mentioned ROP, return-oriented programming. You just put up chains of existing code together and call that by just setting up a proper stack and then changing the stack pointer to point at the right place. Stack canaries, again, the same. You have a read vulnerability. You find the value of the canary. You write the canary at the right place. Boom, you're gone. There are even situations where you don't even need to get code execution in the traditional sense in order to turn a memory overwrite into something useful. So at Kansek West, there was that guy who won the Microsoft IE11 hacking contest, and he had two techniques. One of them he couldn't disclose on stage. So he had 4 or 5 slides that were completely blurred out. And he called the technique vital point strike. But I recognized the dialogue on one of the blurred out slides, and I think I have a pretty good idea of what's going on. So as you might know, in Internet Explorer, you have security settings. Depending on where that piece of JavaScript that's executed is coming from, you might be able to do more or less things, depending on the security zone you're in. Now, what security zone you're in is some piece of memory. What if I can find a way to write to that piece of memory? Boom, God mode. I just set the flag and I can send JavaScript or Visual Basic from my page and everything's executed. My OCXs are executed, code execution. So all the mitigations, they're good. They're making life more interesting to the attacker, but in the end, they don't help. Then there's quite a list of tools you can use to find memory problems, and I started looking at them in a systematic way and tried to find out how good they are, what they can do. You probably all have heard about Valgrind. What you do is you instrument your code. You have a debugging executable where additional checks are inserted, usually based on Garg pages, to make sure you're not writing to memory you're not supposed to. These days, you have memory sanitizers in GCC and LLVM. Again, the same, you compile your program with a special flag, run your test suits, and it tries to find memory overruns. The thing is, both Valgrind and the memory sanitizer use a technique called object-based verification. And I'm getting to in a second why that doesn't cover all of the cases. And so the other ones, Those are attempts to, I talked about that the C semantics allows you to actually carry around information to check every pointer access whether you're still pointing to valid memory. Come on. You're not serious. I've been talking too long. So what they all try to do is take the existing C standard and give a different binary interpretation to provide safety against that. And all those have certain shortcomings, and I'm illustrated for a way. At the moment, I'd like to focus on the object-based versus pointer-based approach. And just so you can follow what I'm explaining, I'll be showing C code that the user writes in black. And all those fancy tools, what they're doing is instrumentation. They insert extra instructions into your binary that check whether your pointer exit is valid or not. That usually happens on an assembler level or on an intermediate representation level in the compiler. But most people don't speak LLVM intermediate representation fluently, so I've chose to not just give that as C code as well. So if you see something in red, that's something the compiler or debugging tool inserted into your code. And you have to think about it as assembler code that's added in the back end or in the optimizer stage, but I write it as C code so you can follow what I'm explaining. So the object-based approach, what Valgrind is doing, what the memory sanitizers are doing, it's essentially this. I use a pointer somewhere. I dereference a pointer either for read or for write, and the code inserts a check where it looks, is the address poisoned or not, and if it's poisoned, an error is reported. So you can think about it as a map that for every address in the system just remembers whether that is correctly allocated or not. So when the program starts up, everything starts out as being poisoned. You say malloc on an area, then that part of memory will be cleared, will be said that's okay, so every access in there is okay. And when you free the memory again the memory is poisoned. This actually finds bugs. So if you have never used Valgrind or memory sanitizer on your C software, you've probably done something wrong because it finds bugs. If you overflow a buffer, right, this stuff will detect it. If you access memory after you've freed it, that stuff will detect it. But there are obviously situations that this stuff will not detect. And one easy to understand example is infrastructural safety. So I have a struct that has an ID and an account balance for my bank account. So that's my account number, say, and that's the amount of money I have in my bank. So when I allocate a structure like that, the complete thing is allocated. So from here to here, all memory is marked as no longer poisoned. But if I have a piece of code that overflows this buffer, I'm overflowing in a different part of the structure. That's still not poisoned. It's still properly allocated memory. So Valgrind won't detect it. Memory sanitizer won't detect it. And still, I can obviously exploit that to change the amount of money I have in the bank, which I think you agree is a bad thing. So, limited approach. The other approach, for every pointer that we carry around, we remember the base address of the object it pointed to in the beginning, and we remember how big the memory area is it is pointing to. So we say malloc of 100, get back an address of 100, and now it ends at 200. So we have a pointer at the address 100, we have a base value of 100, and we have a bound of 200. When I now go to that pointer and add 50, what happens? You have a pointer value of 150, pointing right in the middle of the array, which still has a base of 100 and a bound of 200 attached to it. So now it's still a valid pointer when I try to address it. If I add another 100, my pointer value is 250. Base is 100, bound is 200. So when I try to write now, I know that this fails. So quite a number of the other tools I've listed there use this pointer-based approach. It does have a number of shortcomings though. So suddenly your pointer size changes. which means that your struct layout might change. Some of the tools implement something like that, but they are only able to translate the whole C program as one big piece. So all your software, your complete software stack must be in one single C file, which obviously translates into not being practically usable. So I've looked at all that, and the only existing project that fulfilled all the criteria I wanted to have to actually take that to a production system was softbound CTS. It consists of two parts, obviously corresponding to two PhDs, like that is in academia. Softbound cares about spatial safety, CETS cares about temporal safety. It uses fed pointers, so it uses the model where it keeps track of the base and bound value, but it uses so-called disjoint fed pointers. What does that mean? It means that the base and bound value are kept in a different area of memory from all the rest. That means that your structure layout doesn't change, which, as everybody knows who has maintained a C program that reads binary data from disk, is a huge win if you don't have to adapt the structures that pull apart your binary. So it's usable for real-world code that abuses C-struct definitions to declare binary form, which is a bad thing, but software out there does that. It comes, and that's very interesting, with a proof of correctness that it will catch 100% of the buffer overflows. So every type of memory, of illegal memory access will be caught, according to a pretty simple semantic model of what a pointer is and what C software is. There's a catch to it, but I'm coming to that later. And it's implemented as an LLVM optimizer pass. So it plugs right into the LLVM compiler, so everything that's compilable with LLVM is compilable with softbound CETS. Yeah, more advantages of that. It supports separate compilations, so you can keep your old file structure and library structure. You can compile a library against program. It completely covers all the cases. It maintains source code compatibility. You can just put in C code there. It doesn't need any kind of special annotation or something. And also it comes with a low overhead. So that's probably one question you might have. What does low overhead mean? If I start carrying around bigger pointers, if I start checking pointers all the time, I'm paying with the runtime overhead, right? And so it turns out that your software will get slower by a factor of 2. So you're getting half the speed your software had before after turning on that softbound CTS module that enables all the buffer overflows in your code, which I think is a reasonable trade-off. I mean, people run web servers written in Ruby, so performance doesn't seem to be a problem anymore. You know, just switch on 50 more instances on AWS. I can live with a factor of 2 for not being exploitable anymore. So how does it work in detail? I already talked about the base and bound value in the fed pointer. So if you dereference a pointer, what the compiler adds is a check where the pointer value, the base, the bound, the size of the object that's dereferenced is passed in. You obviously want to take care of the size too, because you might be at the very last byte of the buffer, which is still a valid address, and try to read a 64-bit value or write a 64-bit value, which will trigger a buffer overflow. So that needs to be taken into account. Check is implemented like this. So if the pointer is less than the base value, or if pointer plus the size of a thing is above the bound value, we abort. So anybody who sees the problem in that? Yeah, you win in internets. So that's the part they hadn't proven correct. They only proved their semantic model correct, that will trigger 100% of all bugs and properly call the check function. They neglected to find the integer overflow in the check function. So my first contribution to the project was to actually make it work by adding a check for the overflow case. Yeah, so don't trust proofs, do some tests. So the base and bound value need to come from somewhere. what actually happens inside the LLVM IR is that special variables are generated. So if I have a variable PTR, an additional PTR base and PTR bound variable is generated and initialized with the pointer value and the pointer plus the size of the array. So I know my lower and my upper bound. And if malloc failed, of course, we set the bound value also to null, so that the check fails. If I ever try to access a null pointer, it will carry a null bound with it, and so the check will fail, the program will abort. A couple of more situations that we need to consider. We not only have heap allocation, we also have stack allocation. And the stack allocation case, yeah, again, I take the base address, put that in the base. I take the size of the object plus the base, I'm getting the bound value. It's pretty straightforward, I think. It gets a little bit more interesting, but not by much. If you're doing pointer arithmetic, you take the pointer, add an integer to it, or you take the address of an object in an array, which is the same semantically. The base and the bound value are propagated. So the pointer that we are deriving the new pointer from propagates its base and its bound value into the new pointer value. This, of course, means that you can do things that are perfectly legal by the C standard. Like you can take a pointer to an array of size 100, you can add 300, subtract 250 again, and you have an intermediate pointer that doesn't point to valid memory, but that's totally okay as long as you don't dereference it. So if after doing all the pointer arithmetic, you end up back inside the array and then access it, that's okay, that's valid. Here's a special case that takes into account the problem of interstructural overflow. So if I take the address of some object inside some other object, like that integer in the struct, I need to do a bit of fancy calculation to find the right base and bound value to narrow, so we're not just propagating it from the base pointer, which is a complete structure, we narrow the address range of just the object we took the address of to prevent the overflow case there. That also works for getting the address of an element inside an array, inside a struct. You have to take care of that as well. So here's a problem. As I said, we have a disjoint fat pointer model. So when I have a pointer value in memory and I write to it, it only writes that single pointer. And if I read back, I'm only getting back that pointer. What do I do with the base and the bound value? So inside the function, they're kept in that special variables. If I write a pointer to memory, I no longer can do that. So what we do is, when I take a pointer, read it from memory, I look up the pointer in a table, and in that table, the base and the bound value is stored. So I have a separate data structure, put in the pointer address, and I'm getting back the base and the bound value. Of course, it looks the other way around for storing metadata to RAM. The moment where I write a pointer value somewhere, like here, the base and the bound value inside my table are initialized with the base and the bound values that I carry around from here. Of course, that's not terribly efficient. So the implementation uses a red-black tree, which is kind of okay. But most of the time, it's just better to keep those values around instead of storing and fetching them again. So in the case of function calls, what happens is that the function is annotated. So if I write a function that takes a pointer as an argument, the compiler internally changes that to a function that takes 3 argument values. It means the base and the bound values become extra arguments to the function for every pointer. And of course, on call side, the base and the bound value, which I have around because I have the pointer, are propagated to that function, so they're available in that function as well. So actually having to look up values in a table is something that occurs rarely. It does occur if you traverse data structures, it happens. So there are a couple of loose ends here, which I won't go into much detail. Memcopy is an implemented primitive function inside LLVM, so you have you have to detect a memcopy call and add special checks to that. Global variables need the initialization done, obviously. Function pointers need special care. You end up not being able to create pointers from integers. That's a very interesting thing, a trick that only some people know these days because we usually have enough RAM in computers these days. There's a trick to implement a doubly linked list using only one pointer value for every element in that list. It works like this. You have a pointer to the first element, you have a pointer to the last element. And inside your single field in the structure that is your element of the linked list, you take the forward pointer XOR the backward pointer. So when you're coming in from one side, you maintain the pointer that you came in with, XOR it to the value in the field, and you're getting the next forward pointer. You use that, XOR it, get the next forward pointer, etc., etc. If you're coming in from the back, you can also do that. You take the pointer that points to the last element, you XOR it in, you're getting the next backward pointer, XOR it in, etc., etc., etc. So neat trick, unfortunately, completely breaks this stuff. So that's one of the situations that you cannot reproduce. And I'd say it's dirty anyways, we're not losing much here. Yeah, you have to handle casting unions, you have to handle var arcs. That's all in the paper. In case you're interested, you can look at that. So we have handled the spatial case pretty much. So pointer loads, pointer stores, pointer access, the reference for read, the reference for write. What we now need to cover is the temporal case. And the approach CETS, the part responsible for temporal safety, takes is again one of fat pointers. So again, we have a pointer, and we get two new values, the key, the lock address. The idea here is that the key is unique. Every time I call malloc, the next key value is incremented. So for every pointer, I remember which malloc call that was by incrementing a unique value. And I also have a place in memory, which is called a lock, that I allocate. And I write the key value to that lock address. And also remember it in the list again, because we will need that. So again, fat pointer, we keep around a index value. We keep around a pointer to some place in memory, which we call a lock. The index value is called a key. And the key and the lock are initialized with the same value on malloc. Now, when we call free, the crucial part is this here. To the lock address, we write a special invalid key value. So if we have a pointer around somewhere, we still have a copy of PTR somewhere. It still has the same key value. It still points to the same lock, but at the lock address now we have an invalid value. So access to a pointer looks like that. We check whether the key is equal to the value at the lock address or not, which is the case after we call malloc, and which stops being the case after we call free. So in that case, we simply abort. So this allows us to tell whether a pointer points to some currently allocated piece of memory. You can think about situations like I'm calling free, I'm allocating an object of the same size right afterwards, which comes back to the same address. So two pointer values, same address. They now have different key values. So even though the pointer value is the same, when I later access that memory using the old pointer, it will trigger a fault. So even though technically I'm pointing to valid memory of the right type, it's from the wrong time. So that aborts. Again, we need to propagate the key and the lock address in case we do pointer arithmetic. Same thing here, we just copy that. We have again the problem of when we load a pointer from memory, we have to get the key and the lock address from a special table where we maintain them. And of course, if we write a pointer to memory, we have to remember the key and the lock address for that pointer in our table. Yeah. Globals need to be handled. Globals are always valid, so the case is easy. They're just all getting the same global key and global log address for the key and log address value. There's a catch to that approach, and that is, you might remember, after free is called, the log value is invalidated. What happens if you have multiple threads and you have the threads get scheduled right between the free and the invalidation of the address? You run into a situation where the key value inside the log is still the right one, but free has already been called. So threads don't work yet, but frankly, shared state is evil. It's the source of a lot of subtle bugs and confusion. If you ever try to catch a race condition, you know what I'm talking about. If you ever try to trace a memory corruption in a shared memory setting, you know what I'm talking about. There's a reason Erlang doesn't allow shared state between threads, and that is that message passing is just much easier to understand, much easier to reason about. The same if you look at formal methods. If you try to verify the correctness of a program, that's often easy in the single-threaded case, but in the multi-threaded case, you have to consider the permutation of all instructions, of all possible instructions that could be active at the same time in all the threads. And you get a combinatorial explosion of possible states. So shared state is evil. You might ask yourself, I've been talking about that academic project I found for quite some time. Did I do my own hacking? And answer is yes, I did do my own hacking. Not only fixed the check, I also started at trying to scale that up, because it was your typical university project. You'd literally download a modified LLVM tree where some code has been patched in that wasn't even connected into the main compiler loop, which came with its own top-level executable that would work on LLVM intermediate representation files to do its job. It would have calls to the libc hard-coded inside the compiler plugin. So if you had external libraries that were not instrumented with the checks, you need to translate between, passing 3 values or 1 value to the function. And if you link to libc, it expects 1 value when you pass a pointer. So you have to do that somehow. So that 2,000 lines long list of function names that would need to be wrapped and came with a runtime library that would actually wrap that stuff, etc., etc. So I figured that isn't an approach that would scale, and so implemented function attributes that would allow you for every function to turn on and turn off the calling conventions and turn on and turn off insertion of checks into that. And then move to FreeBSD. Why? Because FreeBSD is a system where executables, if you say make build world, right, it compiles everything from scratch, and it's possible to compile that using LLVM from scratch. So I had a code base where I could make sure that every single line would go through that instrumented compiler that would insert checks for buffer overflows and everything. So I acquired a friend who understood FreeBSD, and we walked through that. We walked through the libc, instrumented the functions that needed to be instrumented, like system calls, like instrumenting the malloc. So because malloc and free, obviously you have to do magic things behind the scenes and generate the values that we did. We deleted the ton of users' wrappers, and we ended up in a situation where a proof of concept now works. So we can compile the C library, compile and link a test program against that C library, run it, and it will successfully be able to make system calls, execute code, and detect buffer overflows. So we have a working proof of concept at the moment. So, demo time. Because you obviously want to see that in action, right? Yes, that one. So here we go. We have a FreeBSD system. We have a small test program. Test program, as you've seen before, you have a buffer of size 16. An argument is passed into that function, and we copy that argument into the buffer without checking the length of the argument passed in here. And here's our main function. So main takes the first command line argument, passes that as an argument to the function foo, which copies it into the buffer. So we can call that. Think about what would you expect to happen if I press return now. So I didn't add any command line arguments. So you would expect the program to crash because it accesses a null pointer, because it accesses a non-existing argument from the command line, right? So if I start that now, we are accessing argv of 1. Argv of 1 is the null pointer because it terminates the argv list. We should see a null pointer exception. So, but instead of a crash, we actually get the debugging output from softbound CTS, which correctly detects here we have a pointer with base, bound, and pointer value of 0. It's not okay to read that, so program is safely aborted. If we do pass in a small argument, let's say foobar, what would we expect to happen? We would expect, access to argv1 should work, right? Foobar is 6 bytes in length, let's say 7 for the terminating 0. We have a buffer of 16. We would expect that to simply work, and it simply works. So what happens if we pass a much too long argument to that? Again, softbound CTS correctly detects a memory safety violation and aborts our program. So yeah, demo successful. Okay, so if you want to look at that yourself, it's up on GitHub. Don't expect to be able to compile it right now without asking me again on what precisely to do, because it's still in a beta session proof of concept stage. There are a number of bugs still in there that I'm discussing with the original author of the plugin. Yeah, I'd like to use the opportunity to thank Hannes for doing the work with me on FreeBSD, and the softbound CTS code authors for bearing with my questions and explaining to me everything, and for providing the source code to the community. So thanks for listening, and if you have questions, I'd be happy to answer them now.
Thank you, Andreas. Do we have questions? Oh, yeah.
I don't know if you have talked about it, but why do you do it in LLVM and not in GCC? It is easier the development, or there is any way that the plugin is easier? Or?
Well, the plugin was already written for LLVM, so that's why I kind of had to use LLVM instead of GCC, so it would have been a lot of work to reproduce it in GCC. And frankly, if you have ever looked at the internals of GCC and LLVM, you want to use LLVM, like absolutely, positively, seriously.
We have another question here.
Hello. Okay, so as far as I understand, we can avoid exploitation of the code, but wouldn't it be better to just, let's say, use this wrapper for example, string copy, and inform the user that the buffer that he put is exceeding the available buffer, instead of crashing application and using abort?
You usually have no safe way of recovering from detecting a memory overrun. So what should you do? Just ignore it? Just don't do anything? So I think just aborting the program is the right solution. So if it's a daemon that runs somewhere, let init take care of starting it again, or whoever, or daemon tools. So I don't think you can find a general, keep your program running solution if you detect a buffer overflow. It's usually better to just abort, because you will have inconsistent state, and you have no idea what that inconsistent state looks like. And I sleep much better if the program is then just rebooted with fresh data.
Do you have more questions? Okay, so thank you very much, Andreas.
Yeah, thank you all for listening.